I'm going to share our poster screen share with you guys so that we can all see what we're talking about. Can everyone see that?
Yep.
Okay, so I think we're ready to get started then. So hello, we're Team Skytanic, and we created the FEV 60, which stands for Flying Electrical Vehicle 60 kilowatt. Although, as always, please note that 60 kilowatt references the full scale version, and we built actually about a 1/30th scale of that version. So the problem that our system was trying to solve is that there currently exist no affordable alternatives to piston internal combustion engines in the experimental amateur build light aircraft category. So there are a handful of off-the-shelf components that are aimed at automotive enthusiasts for electric vehicle conversions, but none meet the safety and redundancy requirements needed for aviation use. So our solution for this problem is the FEV 60, which is a first pass at a modular and redundant powertrain for an electric aircraft. It consists of a motor and its drivers, power systems, and a battery system. It also has a user interface, which includes a throttle and feedback for the pilot on the state of the system, which includes things like faults and errors that might be occurring, or RPM for normal situations. So it provides an alternative to It provides an alternative to internal combustion engines as it is electric. And I mentioned earlier that the system is redundant, and this means that if one module fails, another of its kind can pick up the extra work and keeps the system running, even if at lower power. It'll keep the aircraft from falling from the sky, which is always a good thing. So in all, the FEV 60 provides users with a fully electric propulsion system that can be implemented in multiple light airframes.
Hi, I'm Jason Scheel. Now, why would we want to go with experimental amateur built aircraft, and why would we want to make it electric? So starting off, the experimental amateur built aircraft category encompasses roughly 10% of the United States general aviation fleet. With a market valuation of roughly $16.4 billion, our product is targeting a significant amount of capital, making it economically worth it. Now, why would we go electric? Starting off, the traditional gas engines cost roughly $40 per 1 hour of flight. This is much higher compared to the electric counterpart, which is only $3 per hour of flight. So the benefits of having an electric aircraft are that it's cheaper, cleaner, less need for repairs, and it is more efficient. Additionally, our product will be able to help student pilots as well as amateur pilots, as the introductory cost to these aircraft are much lower, as well as the maintenance costs are much lower. Plus, we have the added benefit of helping the environment.
All right, now let's take a look at our actual system design. So we designed the FEV 60 with redundancy in mind, as Becca was saying. And that means that if any module fails in our system, another one of the same kind can come and pick back up and take over that task. It also means that the system's incredibly modular. So if you need to scale up your power output requirement, you can do that easily by just adding more motor drivers to the system. We designed, again, only a 2 kilowatt or a 1/30th scale model. And that can, again, be easily scaled up to our 60 kilowatt requirement by adding more motor drivers. So let's get into the actual module interaction of our system. So we start off with, on the left, our user inputs. These consist of a throttle, which is just a traditional airplane throttle, and various buttons and switches that allow the user to interact with the systems of the plane. So from there, we move on to our battery systems. Those consist of our battery cells and battery management systems. This is really an important part of our plane because, again, this is an electric vehicle. These all feed our low voltage power systems as well as our motor drivers. The low voltage power systems feed all of our low voltage systems. They supply 24 volts to the entire plane, which this is a very common voltage output on aircraft. So you can easily add in pre-made systems such as GPS to your cockpit. Moving on, we then have our motor drivers, and these consist of a gate driver as well as an MCU. And these just deal with the phase output brushless DC motor. And then finally, we have our IO MCU, which this takes all of our user inputs and sends that throughout the system to make sure that the plane is operating properly. And it also receives feedback from all of our modules in the system to detect any faults. And if any faults are detected, those will be displayed on our LCD, as well as an annunciator panel to let the pilot know if there are any system issues.
So moving on to our actual hardware, you can see our main PCB modules down the bottom of the poster. So to start, our I/O board that Trent was just talking about is in Figure 4, the top left of the boards. This board interacts with the whole system and gains crucial information about like battery percentage, state of all the modules, and all the information a pilot might need to fly the plane properly. This connects to all the system with a DB25 connector. We learned throughout this project that the DB connectors are very important for the aerospace industry because they can be manufactured and connected in such a way that they can withstand vibrations very easily, and they're pretty modular and easy to switch out boards, which is why we wanted to make so many modules for this system. The I/O board also interacts with a LCD character display that the pilot can interact with using the buttons on the board. And again, as Trent mentioned, an annunciator panel that allows more quick and more in-your-face warnings if anything goes wrong.
All right, moving on to Figure 5, which is in the center top row of the PCBs, is our low voltage power module. So this is a buck converter that can convert up to 120 volts down to 24 volts. This 24 volts, which is now at a safe level, routes to the other boards on our PCBs, powering our I/O board and our motor driver, as well as having the benefit of routing to the cabin of the aircraft where 24 volts is often needed for the instrumentation. During the development of this, we learned many of the fundamentals of power electronics and the effects of switching and heat dissipation throughout our system.
All right, now moving on to Figure 6, you can see our motor driver board. This is sort of the workhorse of the whole system. This again incorporates our DB connectors. These are DB9 connectors, and again, as Ryan was saying, they're very resilient in the environment of an aircraft. So we have, again, our MCU and our MCU power systems on the left. These are all our low voltages. This is all fed by the 24-volt board. And we also have 2 more dedicated rails, or 3 more dedicated rails, a 12-volt rail, a 5-volt rail, and a 3.3-volt rail. The 12-volt rail feeds all of our phase controlling outputs, whereas the 5-volt rail actually controls the Hall sensors of the motors. These Hall sensors deal with the timing of all of our phases. And then we have our 3.3-volt rail, which deals with all of the MCU operations. This is our logic level systems. And so on the left, you can actually see our phase outputs. These are all fed again by that 12-volt rail. And these take our 100-volt or whatever working battery voltage we have and sets those into 3 different phases that are then sent to the motor itself.
And the final PCB is Figure 7, the battery module. The battery module combines all the different parts of the battery management system onto one board. Battery management systems are complex, and designing one from scratch is a complete senior project in itself. Since this wasn't the focus of our project, we decided to try and find something to buy and integrate into our system. But there's no 30-cell BMS modules or a 30-cell charger that was within our budget that we could buy. So to work around this, we got 5 independent BMS modules. That's what those 5 hexagons are. And each one of them protects 6 cells. So in total, putting them in series, we get our full 30 cell battery. This was helpful for charging them as well, because it was a lot easier to find a 6-cell charger where it only needed to be able to charge 6 cells versus a full 30 cells. And so we could find one that was within our budget. And so without further ado, let's move on to the demonstration part. I'm going to show the battery module.
So at this point, I'm going to stop sharing our poster so that it's easier to see the video feeds of the actual demos of our system. So.
Everyone see my screen?
Yep.
Okay. So this is the battery module system, the BMS. Each one of these is a BMS that has 6 cells connected to it. There we go. So that's what it looks like. On the right here, we have a circuit breaker. And that's what the battery cells look like. By flipping the switch, we can see that we get our full 100 volts off of the battery system.
So now that we've seen what the batteries can do, how they're integrated together, now we can look at the rest of the system, which is at my house. And due to the coronavirus, we couldn't really combine these systems, but that is basically what powers the rest of our modules. So to start, we have battery board powering everything else around here. So we have our 2 redundant motor drivers, which are connected to our motor and our throttle. And these are also connected to our 2 24-volt submodules that take the battery power down to a usable level for the rest of the boards. We have our I/O board that interacts with the system with its big DB connector and the annunciator panel and the LCD screen that this interacts with. And together these make a complete system that interacts on many different software levels, which Alex will now talk about.
Right, so because of the coronavirus and the way things were set up, we couldn't access our high voltage power supply, which means we couldn't test or be confident in our boards that they weren't going to fail when connected to the batteries. And because of this, to keep things safe, we couldn't connect to high voltage. So this is purely our low voltage level. So the power supply he has on is at 24 volts, and it's bypassing our 24-volt buck modules and just giving 24 volts to the whole system. So if he looks at the LCD here, you'll see that it says a 24-volt fault. That's basically indicating that the 24-volt bulbs aren't seeing high power and not outputting 24 volts of power. So the I/O board's seeing them as a fault, which is expected with this current setup. It's also saying that RPM 0, which is consistent with the fact that the motor's not spinning right now. And so if he spins the motor, if Ryan's able to spin the motor here real fast, you should see the RPM change a bit. So you're seeing some sporadic values because when you spin the motor by hand, it's fairly sporadic in the speed at which it's turning. So that calculation can't average out and get legitimate value. If we were able to test it with actual steady state values, we'd be able to actually hone in and get a more legitimate value on that. And so now if he flips a switch on the I/O board that turns on the motor, basically, you'll see it indicate that motor's on. And obviously, since we don't have high power connected, the motor's not going to spin at all. And there's actually nothing enabled, but it's just a software side of things to allow you to actually spin the motor. And that's more or less what it's saying. And so what's going on if he turns it back off it'll say motor off, and that'll indicate to the user that if high power is connected, moving the throttle wouldn't actually do anything. And so if he moves back to the motor and the throttle, if you can show that, our sponsor Harut actually 3D printed that for us. And all it is it's a potentiometer that we've connected to the ADCs on both of our motor drivers. And that just gives you the speed of the whole system, or to control the speed of the motor. And we were able to, when we could connect to power earlier in the semester, where we were able to spin the motor both with one and with both of the motor drivers. It's just we're having some issues with it, and it was inconsistent. We were blowing some things up. So with the new version of boards, we didn't want to test that with the batteries because we weren't sure exactly what problems we were going to have. And if he spins the motor again, you can see there's lights that light up on the motors. And that basically is the Hall effects that are feedbacks from the motors spinning, flipping, showing that there is feedback coming from the motors. And that's how we calculate the speed. There's a calculation I won't get into, but it's basically every so often you can time the amount of time the Hall effects trigger and you get speed. And those are sent through serial bus, which you can see in the middle there. Well, there's a lot more than just the serial bus, but as part of our harness, it sends serial communication to the I/O board, which is then displaying information to the screen over SPI. One of the bigger problems we had towards the end of the semester was when we're switching the high voltage, the 100 volts or higher, or in that range of voltage, both on the 24-volt board and on the motor drivers, it creates a lot of noise in the area. And with that current setup of the harness, you get a lot of problems with communication just due to the noise you're creating in the loops in there. And so something we were trying to work on when this whole thing happened was creating a more streamlined harness, but we couldn't test our noise problems because we didn't have the high voltage power supply, so we couldn't make much progress there. In addition to the noise caused by that, it also causes voltage on those lines to get above the rated maximums of the microcontroller. So at the moment, we're just using 3.3 volts logic level of the microcontrollers to communicate between the systems, which is good enough on this low of a scale, but at a higher scale, we'd use a more robust system like RS-485. So we had to implement opto-isolators and diodes to prevent our microcontrollers from blowing up. And throughout this whole project, we also learned a lot about power electronics and power electronics design. And we got to thank Professor Maximovich for that.
Another big thing that we learned throughout the process of this project is we learned a lot about the aerospace industry and the aircraft world. And so we'd like to take this time to thank our sponsor, Harut, because we knew absolutely nothing about aerospace or aircrafts going into this project, so we would have been completely lost without him. So thank you so much, Harut, for all your help and guidance.
Absolutely. Thank you for all the hard work.
Okay, that's basically it. Do you have any questions for us?
Well, good presentation, first of all, guys. Seems like you guys got some awesome progress done on your project. Definitely very cool to see that. One question I had, and I might have missed this, when you were talking about potentially doing more robust communication in future iterations, did you have any issues on this prototype with any serial communication interference from like the switching mode power supply, or any issues talking with the microcontroller?
We had it when we ran on high power, we did have some problems, and that's what I was discussing with the serial communication. When we're switching the 100 volts and the 24 volt and our motor driver, we did have some noise problems, and that's what we were trying to fix a little bit with a better harness and maybe with a more robust communication like RS-485 that could help, but we were still experimenting with that. From the actual plane system, you'd use RS-485 probably because it can go longer distance than just the 3.3 volt logic level UART system that we're using.
Cool, yeah.
So since you had the whole coronavirus, I know you talked about the wiring harness, respinning the board. Is there any other major things that would need to happen for your project to be completed as intentionally had?
So, or someone else can answer because I'm talking too much. But
So we also had some plans to do some actual power output testing of our actual motors. And that would have involved some pulley systems and some weight moving versus time measurements just to figure out how much power we were actually getting out of our motor, because that is an important part of our system. We need to meet that 60 kilowatt requirement. And we also had some requirements for whether or not the system was viable for an hour of flight time. So that involved having the right amount of power for takeoff, the right amount of power for cruising, and the right amount of power for landing. And on top of this, we also needed to figure out if our batteries had enough lifespan to make that hour time. So we unfortunately didn't get to test these things, but I think had coronavirus not happened, we would have gotten a chance to work on this.
Cool, thank you.
If you were to put a percentage on where the project got to in terms of what was initially conceived, where would you place that?
In terms of brunt work done, I think we got pretty far. I think we got above 90%. But the last 10% or so we have left is a lot of fine details that are very critical to the success of the project. And so I would say we got very close to determining if the project was feasible with the way we set it up. The way our plan was to have parallel motor drivers running, which is after talking to Professor Maximovich and other power electronics people, it's not necessarily the best way in terms of reliability and redundancy to do things. A lot of other aerospace applications just use fallback systems. So if one fails, there's a backup that's not on until the first one fails. And that's a little bit more reliable, and it's done in all of aerospace. It's pretty common to do. But as part of the challenge of this project, we wanted to try to do the parallel motor drivers. And we think that would have worked, but in the full scale version, we're not sure that's the actual best solution based on what we found and the problems we were having with getting both motor drivers to work correctly together. So I don't know if I answered your question. I don't even remember what it was.
Yeah, I think you did.
So, okay.
We've got like 1 minute before we're gonna have to finish up. Harut, do you have any questions for the team?
No, I would like to say it's pretty exciting to see the progress that you've made, and especially considering the circumstances with the coronavirus, the goals that you've taken on were pretty ambitious, and I think you did really well under the circumstances. And I wouldn't feel too terrible about not being able to test the power output or some of the other aspects of your project. It's still exciting to see everything connected together and working at the very end. So good job, and thank you for all the hard work.
Yeah.
We appreciate that.
Yeah, good job, guys. As I'd love to say some more things, but we got to move on to the next thing. So good job, guys. Great presentation. Thanks for a great year. This was fun. I hope you guys got a lot out of this. It sounds like you definitely did.
Yeah, we learned a lot. Thank you.
Cool. All right, guys. Thank you so much.
Thank you.
Have a good day.
Thank you.